Good morning, everyone. I'm Percassi Francesco, and welcome to this talk. The work I'm going to present is a collaboration between the University of Brescia and the University of Huddersfield. Hybrid models are advancing models describing dynamic systems in which there is a discrete and a continuous component. PDDL Plus is an expressive formalism that allows defining hybrid models in the context of automated planning. One of the strengths of this formalism lies in the clear separation that exists between the scope of the agent and the scope of the environment. The PDDL Plus construct introduced to model the environmental changes are processes and events. A PDDL Plus task pi is a tuple in which f and x are the set of propositional and numeric variables. I and g are the initial and goal state. A is the set of actions, and finally E and P are the set of events and processes, and they are the PDDL Plus part of the task. Informally speaking, solving pi consists of finding a sequence of actions over a continuous timeline in order to transform I into G, while conforming to the discrete and continuous changes brought about to the state of the world by events and processes. In this work, we start from a translation scheme, namely Poly, recently published at KEPS, proposed for discretize a PDDL Plus task into a numeric one expressed in PDDL 2.1. In particular, Poly satisfies the properties of soundness and completeness according to the discrete PDDL Plus semantic. Starting from Poly, we propose a variant, namely Poly minus, that produces a lighter encoding at the expense of completeness. Processes are used to model the exogenous and continuous changes of numeric variables, which occur outside the control of the agent. Consider the PDDL Plus car domain where a car has to reach a specific position. In this domain, the velocity and the position of the car change over time according to what prescribed by the process displacement car, whose PDDL Plus syntax is shown on the left. Such a process expresses the following semantics. When the engine of the car 1 is running and the time passes continuously, then the distance and the velocity of the car change according to these two differential equations. Events have a similar structure to the processes, with the difference that the changes are discrete and point alike with respect to time. In this case, when car reaches a critical speed, the engine explode event is triggered, setting the positional variable crashed to true and the acceleration to 0. Now we revise the Poly scheme. In Poly, the simulation of the passage of a discrete quantity of time takes place by executing a sequence of actions consisting of the tuple start, any permutation of the AP actions, followed by the end action. We explain this scheme by means of a small example. On the left, we have a partial PDDL Plus plan for the car domain having the displacement process. In this plan, there is an acceleration followed by a pause of 1 second, during which the active processes flow. The corresponding PDDL 2.1 plan for the pi-poly problem consists of the start action, which blocks the execution of anything outside the novel actions, followed by the sim displacement distance operator. This operator affects the position of the car according to what prescribed by the discretized displacement process, if its precondition hold when start is applied. Such action is followed by the sim displacement velocity operator, which has a similar structure to the previous one, except that it affects only the velocity. Finally, the simulation is closed by means of the end action only whenever all the AP operators have been executed, thus making all the action applicable again. In the Poly minus scheme, the simulation of a discrete quantity of time takes place by performing a single action, that is, simulate. Simulate is always executable and has a conditional effect for each continuous effect of each process of the task. Given a single continuous effect, each corresponding conditional effect has as activation condition the precondition of the related process, and as effect, its discretized formula. Observe that poly minus is incomplete in the general case because, given a state in which simulate is applied, more conditional effect affecting the same numeric variable could be activated, thus generating an undefined successor state according to the numeric semantics. Now we can define a simple syntactic property that we call mono left-hand side in order to guarantee that the poly minus translation is sound and complete according to the discrete PDDL plus semantics. We say that PDDL plus task pi is mono left-hand side if it does not have two processes having a numeric continuous effect affecting the same numeric variable. So, given this definition, we can state that if such property hold, then pi poly minus preserves the solution space of pi. And if this property does not hold, then pi poly minus can be unsolvable even if pi is solvable. In our experimental analysis, we compare the poly with the poly minus using the same numeric planner, that is metric FF. In this table, we have reported the results we got in terms of evaluated nodes and search time, indicating with a cross mark which domains are not mono left-hand side. We can observe that in the mono left-hand side domains, poly minus is always preferable or comparable in terms of the considered metrics, while the domains UTC and the linear generator become unsolvable using poly minus because they are not a mono left-hand side. In Baxter, despite it is not a mono left-hand side, it is possible to find a solution faster, but by doing more exploration. This additional exploration is due to the fact that poly minus introduces some search constraints due to its incompleteness, preventing those states in which more than one conditional effect affecting the same numeric variable are triggered from being visited. We have designed a basic portfolio to combine the benefits of both schemes, which we have called Polystar. In Polystar, we use poly minus if the considered task does not satisfy the mono left-hand side property, while we use poly in the other cases. We compare the poly minus, Polystar, and NHSP, which is a planner that natively supports PDDL plus, in this survivor plot, showing how the coverage evolves over time. We can see Polystar works better than single translation schemes because it quickly converges to the higher coverage. The time gap between NHSP and the translation-based configurations is due to the translation overhead. For concluding, we have designed a novel translation for discretize a PDDL plus task into a numeric one that is sound but incomplete in the general case. Poly minus generates more compact encoding than poly, but it is complete only over a subclass of PDDL plus task. Experimental analysis shows that poly minus can make the search lighter, and therefore that it is possible to obtain a more efficient translation scheme than poly. So, thank you for your attention.